discuss in detail about the nuclear shell model, and I will give you some shortcuts, some important tricks. So with those tricks, you can be able to solve any question related with shell model very easily. So we will start with our topic, the stability of these magic numbers and what are the various experimental proofs. So which favor that. So these magic numbers are some special numbers, and for these particular magic numbers, so if the neutron or proton, so it is having a magic number, so those nucleons, so they are showing some sort of different identity as compared to their neighboring nuclei. And then we will discuss how this idea of magic number, it starts the origination of this nuclear shell model, and how the people start to think that the nuclear, it is not something like a liquid drop, so which is the collective motion of these positive particle and negative particle. So they find some other way to more number of isotopes as compared to their neighboring nucleons or protons. So they are having larger number of abundance number of neutron 82, their relative abundance is 82% as compared to their neighboring nuclei. So the magic number like lead, so they are having very high number of isotopes. So isotopes and isotones of protons and neutrons, so they are very high in number. Apart from that, so the neutron absorption cross section, it is very low for the nuclei which is having this magic number. And the quadrupole moment of some nuclei, it is found to be zero experimentally, which shows that some nuclei, they are tightly packed, some nucleons, they are having some elliptical form, some have spherical form. So all the nuclei, they do not have only the spherical shapes. So these are some of the features of this magic number. Now if you check from this graph, so this graph, it is showing that the cross section for this neutron absorption, it is much lower for some nuclei. So like if this is the trend of the graph, you can see it is increasing. But for these nuclei, so they are lying below this graph. So their cross section, absorption cross section, it is very low as compared to their neighboring particles. So like, so it is very low as compared to their neighboring particle. So later the people give the explanation that, so these nuclei, these magic number nuclei, they are tightly packed. So tightly packed nucleons within the nucleus. So due to their tightly packed, so they are it is very difficult to add some proton or neutron, or to eject some proton or neutron from these stable nucleus. So this is one of the regions. So the people, they give some idea, so why these some nucleons, so they are behaving differently as compared to other nuclei. So this is another feature. Like the energy of the excited states, they are very high as compared to their neighboring nuclei. So this is the magic number nuclei, their ionization energy, that is the first ionization energy of magic number nuclei, it is very high as compared to their neighboring nuclei. So this also gives this idea that, so they are having some sort of nucleons, they are packed in some certain way, so which is showing their extra stability. So this showing the extra stability of nucleons for this magic numbers. So this another trend of this graph, so the difference in the energy between experimentally and theoretically calculated with the liquid rock formula. So you will see that, so the lower atomic nuclei, so their energy is quite different as experimentally as compared to the energy which is being explained by these liquid rock model. So this different in energy, like this strand, it is somewhere here. So this is somewhere here. So this energy, so there is quite variation in energy for this lower atomic nuclei. So this is the reason. So they give some idea to people that the nucleons, so they are not something like a liquid drop, or there are some other type of models that they need to design in order to explain this nucleon interaction within the nucleus. So this trend, it is also showing like that the binding energy curve, it is increasing, decreasing, and then it starts to increase, then it decrease. So this is, so these nuclei which is having the very high binding energy or high ionization energy as compared to their neighboring nuclei. So this paper has been published, so which also explain the existence of these magic number nuclei. So this is again the trend. So we can find out the separation energy. So they have found out the separation energy. Actually, the separation energy is the minimum energy needed to separate one neutron or proton from a nucleus, and they found that the separation energy for these magic number nuclei, it is very, very high as compared to their neighboring nuclei. So these are some of the experimental proofs, so which give the hints to people that the nucleus, it is not only a liquid drop, and there are some sort of other effects they have been experimentally proved. So they changed their approach. So in the liquid drop model, so they have considered using the macroscopic approach. So they need to identify, or they need to change their macroscopic approach to microscopic approach. So for which they are trying to drive a model, so something like this way. So in this liquid drop model, you can see that they say that it is something like a viscous fluid in which some sort of electrons which are randomly distributed and positive charged particles, so they are randomly distributed. So in this shell model, so they said that there is some sort of interaction within these nucleons which exist, and based on these nuclear interactions, so they derived out a model, so that is known as the shell, single particle shell model. So since in the starting of this single particle shell model, so they have considered some assumptions. So what are those assumptions? So they have considered that there is not any type of interaction which exists between these nucleons, and they have considered the approach for only a two-body problem. Because if they take the many-body problem, then it will be very, very difficult to drive or to generate the Schrodinger wave equation individually, and this phenomena, it becomes a complex approach. So they considered some of the assumptions for this shell model. So it is based on the independent particle shell model. So in this, they have considered that the nucleons, so they exist in the form of a shell. So the nucleons, so they are having some sort of discrete energy distribution, so not a continuous energy distribution. So they consider the discrete energy distribution for these nucleons. And there is some sort of collisions, and due to these collisions, so some neutrons or protons, they are exchanging their energy, and due to that, so there is some sort of spin angular momentum and orbital angular momentum which exist between these nucleons. So these are some of the assumptions. So until that, the quantum mechanics, like the Schrodinger wave equation, it was already present because in 1925, and the Heisenberg uncertainty principles. So a lot of discoveries has been made on. So they also added the quantum mechanics approach for this shell models. So what they considered is the nucleons, they are considered as the quantum objects, and only they have some sort of discrete energy values. And since you know that these nucleons, they are fermions having half integral spin, so they are following the Pauli's on a Pauli's exclusion principle that the two nucleon, they cannot occupy the same quantum states. So you can check from this that the neutrons and protons, so they are explained separately for this discrete energy distribution, and these neutrons, so they interact with only the neutrons, and the protons which interact only with the protons which are present within the nucleus. So this shell model, it has been first explained by Elazar in 1933. Later, this model, it has been modified by Mayer, so Geoffroy Mayer in 1949, and three other scientists, Swiss, Swiss, and Jensen. So they independently published two papers in the same year, 1949, so which explained some sort of spin orbit interaction. So there is some sort of interaction which exists between this spin quantum number and this azimuthal quantum number, and due to that they derived some sort of another quantum number that is known as the total nuclear quantum number. So these model, so due to this spin orbit interaction, so they got the Nobel Prize in 1963 for this discovery. So in 1963, they got the Nobel Prize for this discovery of shell model. Now, what are the major points for this shell model? So they considered the analogy of the atomic model. So they use the same model, so as the atoms in the atomic models, the electrons which are present in some sort of shells. So similarly, they considered that, so the nucleons within the nucleus, so they are also present in the form of shells. Something like the same model, S, P, D, F, all these subshells. So similarly, so they are occupying like this subshell S, it is occupying 2 electrons. So then these two subshells, 2s and 2p. So this 2s, it is occupying 2, 2p, it is occupying 6 electrons. So total, so they are occupying 10 electrons. So these are some of the atomic model which you have studied, like the Bohr-Sommerfeld model. So they use the same analogy for these nucleons which are present within these nucleons. Now, if you check this nuclear models, now what they said, that the nucleon in the nucleons like the neutrons and protons, so they are interacting independently. So you can check that the nucleons, they treat individually, and it is assumed that the nucleons, they do not interact with each other. So the proton, it is not interacting with the neutrons, and similarly the neutron, they are not interacting with the protons. So this analogy of this atomic structure, so the explained this nuclear shell model, so the individual nucleons, so which are behaving independently within this nucleus, and there is some sort of average nuclear potential which is being generated, and they considered that, so these independent nucleons, due to their movements, there is some sort of average pseudo nuclear potential which is being generated, and they give those potential as the nuclear potential, and from that nuclear potential they find out the energy, various energy states for these nuclei, and for their discovery they got this Nobel Prize in 1963. Now, what are the major obligations of this nuclear shell models? The nucleons, they exist in quantized energy states. So like they are existing in the form of pairs because they are fermions. So each state, it can have either 2 proton or 2 neutron. So they must have opposite spins. So in order to have a stable balance, so they must be present with opposite spins. and if one nucleons in this first state it is with up spin, then the nucleon that will occupy with some anti-spin in order to stable or in order to cancel those spin. So these set of allowed states for protons and different for neutrons. So proton and neutrons, so they are occupied within this nucleons separately. So protons, so they are making their separate space within the nucleus. The neutrons, they are making the separate space. So the set of these allowed state, they are different for protons and different for neutrons. So they using this Schrodinger wave equation, and from this Schrodinger wave equation they derive the energy values for that particular equation. So they find out the solution of this Schrodinger wave equation, so using the spherical symmetric central field of force, and from that they have find out the energy eigenvalues and energy eigenstates, and from these energy eigenvalues they find out the discrete energy states of all the nucleons which are present within these shell structures. So I will not explain all about these Schrodinger wave equation, so but the basic idea is they started their model using the time independent Schrodinger wave equation. So this is something like a nuclear potential, so they have considered, which is due to these independent nucleons. Now this nuclear potential, it can be of any type. So the various people, so they used different approaches. So some used square well potential, some used rectangular potential in order to find out this energy of these nucleons. Some use Woodson section potential, some use exponential nuclear potential. So by putting these values differently for different models, we can find out the energy eigenvalues for this solution of this Schrodinger wave equation. So if you try to look at in this slide, so what they have found? So they have found that the energy eigenvalues, so this equation, it is very important. So can you see this equation? So E, so I will write it here. So E, it is coming out to be of the order of n plus 3/2 into h bar omega. So in some books this n, it is written in terms of lambda. So this lambda, it is a very important factor. So this lambda, it is known as the degenerate oscillator quantum number. So this degenerate oscillator quantum number, so this lambda, it is basically dependent upon 2n plus L minus of 2. So it is dependent upon this principal quantum number n, and it is dependent upon this azimuthal quantum number L. So based on these values, they find out this degenerate quantum number, and based on this degenerate quantum number, they have found the different energy states for these nucleons within this shell model. So from this table, so this model, it has been first explained in 1933 by Swiss, and later this model, it has been modified. So when the value of this n, it is equal to 0, so the minimum energy of this nucleons, that is known as the free energy state, so that is of the order of 3/2 h bar omega. So this is written here. So in that case, only those nucleons are present, so which exist in this subshell, that is in 1s orbital. And from that you can calculate total number of nucleons which are present in 1s. So that is it, from you can calculate from this equation 2l plus 1, 2l plus 1. So L, where L is representing the principal quantum number whose value is from 0, 1, 2, 3, so and so. So 0, it is for s orbital. So if the nucleon it is present in p orbital, then L will be 1. If the nucleon it is present in the f orbital, then L is 3. And if it is present d, so this is d and this is f. So if nucleon it is present in f orbital, then L is 3. So and so you can find out the number of nucleons, and this is the very important table. So I have just kept it. So based on this value of n and L, you can find out. So when lambda is 0, so in that case only this term it is valid. So and this term is when n is 1 and L is 0. So that is having only one s value. And when n is 1, so when n is 1, so only this case is valid. So here n is 1 and L is 1. When n is 1 and L is 1, so that when L is 1, it means the nucleons, so they are present in this p orbital. So that's why here these higher energy after 1s it will be 1p, and when this n is 2, so in that case you can see, so I have made this connection. So what does it mean? So these two different energy states, so these two states, so they will have the same energy value. So what is this 2? So 2 is when n is 2 and L is 0. So when n is 2 and L is 0, so that case is known as 2s. And second state, when n is 1 and L is 2, that is known as 1d state. So the nucleons, it will be present in this energy state, and how many nucleons maximum they can be occupied within this state. So for example, in S state there can be only 2 nucleons, and in D state so there can be 10 nucleons. So total nucleons in this state is 12. So here in p orbital, number of nucleons which can be occupied, that is 6 nucleons. So similarly for higher energy states, you can find out the value of these nucleons. It is coming of the order of this way. So this model, it successfully explained about this first term. So why these 3 terms, so which are known as the magic number. So why the magic number nuclei which are considered to be having exceptional stability. So they have explained that why these 2 it is more stable as compared to their neighboring nuclei, why this 8 it is more stable as compared to. So but they fail to explain these terms. So this model does not fit for these terms, because we have known that the magic numbers, so they are 2, 8, 20, then it is 28, then it is 50, then it is 82, then it is 126. So these numbers, so they are having no connection with the magic numbers. So later, in order to explain this model in more detail, so what people say, so this is the same thing which I have explained in my previous slide. So how you can calculate from this table the total number of nucleons for each shell, how many nucleons it can be present. So there explains the spin orbit interaction. So you can see from this graph, so when the energy is of the order of 3/2 h omega, so in that case when n is 0, so only one s state it will exist. So one s state it is having only 2 nucleons. So when n is equal to 1, so in that case, so there is having 5/2 h bar omega energy. So p nucleons, so nucleons will be present in p orbital. So these 2s and 1d, they are having the same energy. So they are showing separately how the nucleons, so they are lying within each this shells. So from this graph, so using this harmonic oscillator problem, so they have distinguishedly written that, so as the number of n it is increasing, so the energy values of these nucleons it is being changing for each case. So like here it is 1s, here it is 1p, here it is 2s and 1d, they are having the same energy state. Here 2p and 1f, they are having the same energy states, and from that you can calculate how many nucleons which are present within these energy states. So later on, so they explain about this spin orbit interaction. So there is some sort of interaction which exists between this spin quantum number and orbital quantum number, and due to this interaction, so they find out another term, that is the total angular quantum number, whose values it can be L plus minus S. So depending upon, so if the spin it is having plus 1/2 value, then we will consider it as L plus S. So if having down spin, then we can consider it as L and L minus S state. So they further divided. So like in the previous slide, you will see that, so they have explained that in p orbital there can be only 6 electrons or 6 nucleons which are present. So they further break down this p into 2 sub shells. So 1p it is having 3/2 energy, and 1p 1/2 energy. So this 1p 3/2 it is having 4 nucleon, and 1p 1/2 it is having 2 nucleons. So this you can calculate from 2j plus 1 value. So j is representing, what is the value of this j? So if j is 3/2, so then you can multiply here. So in 1p 3/2, so there will be 4 nucleons which are present, and similarly in 1p 1/2 you can see that there are only 2 nucleons which are present. So for each cell, so it is further broken into 2 subshells. So one is having L plus S energy states, and one is having L minus S energy states. So based on that, so they see that, so this, when this 1f orbital, so whose lower energy, that is 1f 7/2, it is very, very close to this lower energy values, and due to this, that, so there is 8 nucleons which are being separated. So that's why this 28 number nuclei which is also stable. So further they calculated and they found that, so they successfully explained why these number, so like 50 and 82 and 126, so they are due to the exceptional stability, because their nucleons, so they are completely filled, and from this energy level diagram you can calculate for each case. So what is the difference between these atomic shells and the nuclear shells? Now you have studied that the electrons, they are bound to atoms by electrostatic force, but in the nucleus, the nucleons, so they are bound to the nucleus by nuclear force. So this is the major difference. Atomic shells, so they have a core, so like the atoms, so the electrons, so they are surrounded by the nucleus, while in the nucleus there is no any core which exists within the nucleons. So there is some sort of independent interaction potentials, and due to those potentials, so these nucleons, they are interacting with each other. So electronic shells, so they are filled by electrons, while the nuclear shells, so they are filled separately by protons and neutrons. Now this is very, very important. So if you have studied the Bohr-Sommerfeld model or the vector model, you will see that the energy of this J, which is L plus S, whose value is greater as compared to L minus S energy states. So what does it mean? It means that in the atomic spectrum, L plus S energy, it is having are lying on the upper level, while L minus S, it is lying on the lower level. So it is opposite in this nuclear shell models. So when you study this nuclear shell model, you will see that this L minus S, it is having lower energy as compared to L plus S. So it is opposite as compared to atomic model. So this is the major difference. So when you draw this energy level diagram, you will see that you will draw L plus S. So they shells are firstly occupied, and this lower energy L minus S shells, so they are laterally occupied. So there is a trick to remember how these, because if you look at this energy level diagram, it is very, very big, and you cannot remember after 1D there is 2S, then 1F, then and further within these there is some sort of interfusions. So like the energy of this 1F 5/2, it is higher as compared to this 2P model, although this 2P model it is lying above this 1F. So but there is some sort of interunion which exists, and it becomes a very complex phenomena to remember this. So there is a trick how you can remember this. So that is spuds if pug dish of pig. I repeat again. So you can write these statements. Spuds if pug dish of pig. So what does it mean? So it means spuds if pug dish of pig means eat potatoes if the pork is bad. So it's better if you are thinking that it is smelly, so you can eat better to cheaper price, or so you can remember this statement, and then you can remove all the vowels which are present within this statement. Like U is a vowel, I will remove it. I is a vowel, I will remove it. U is a vowel, I will remove it. In dish, I is vowel. O is vowel. So after the removal, so what I can write? S, P, D, S, F, P, G, D, S, H, F, and this pig is written as it is. So then you can make a group of 6. So from this, I make a group of 6, and this is again, I make a group of 6. So in this first case, so there will be interunion which exists between S and D and P and F. So there will be no interunion, so you will write it is as it is, and again at the last there is an interunion between G and I. So by this way you can remember this. Spuds if pug dish of pig, and you remove all these vowels from this sentence, and you can remember this sequence, how the nucleons, so they are occupying within this higher energy, how the energy is being occupied within these nucleons. So you can check from this S, this sequence, S is filled, then P, then D, and there is a fusion between D and S. You will see that this 2S, it is lying in between D 3/2 and D 5/2. So as I have told you earlier, L minus S, it is having higher energy as compared to L plus S. So 1P 1/2, it will be at the upper energy state as compared to 1P 3/2. So similarly, 1d 5 by 2, it will be at the lower energy state as compared to 1d 3 by 2. So this is the major difference between this atomic model and the shell model. So there is a interfusion between this D and S, and after S, so there is F. You can see this sequence is the same as I have explained you, then P, then G, and then D, S, and H, D, S, H. And there is no any interfusion between these energy states. And then after H, there is F and P. So this is how you can find out the energy or the number of nucleons for each energy states. So suppose I want to find how I can explain the ground state.
Hello, sir. Hello, stay there.
Nucleons. So first 10 in one. Hello.
Hello, sir.
Am my voice is audible? I have connected it through mobile. I think let me change my connection. So you will see that how these. Sorry, shall I start?
Yes, sir.
Okay. So you will see that, so if there are 10 protons, how these protons, they are being occupied within these shells. So 2 protons, it will be occupied in 1s 1 by 2, and then they will be occupied in p orbital, and first it will be filled 1p 3 by 2, then it will be filled 1p 1 by 2, and you will see there are 2 protons. How many protons you can calculate from this 2j plus 1. So by putting the value, you can see that in 1s 1 by 2 there are 2 protons, here there are 4 protons, again here there are 2 protons. So they generally add up all these 3 and they find out this number. So there are 10 protons, so these last 2 protons, so then they will go for the higher state. So SPD के बाद जाता है, so P के बाद आता है D, so D will be 5 by 2. So similarly you can calculate, so we will now solve some numerical problems, and this is how you can calculate it for the excited states. So suppose this is for the ground state, and one of the nucleons, it will be jumped from this last energy orbital and it goes to the nearest upper energy level. So when it is being asked that find out the excited state, so there is more probability that it will jump to their immediate closest energy level. So that is like if from 1d 3 by 2, it will be jumped to 1f 7 by 2 level. So this is also, you can find out the excited state energies for these nucleons. So applications of shell model. So important applications of shell model, we can find out the spin and parity of the ground state nuclei. So we can find out the spin and parity. So for even nuclei, even nuclei means, so if there are even number of protons and even number of neutrons, so when there is even number of protons and even number of neutrons, so each one is being paired up. Like if it is present in p orbital, p3/2, there will be 4 nucleons, and each nucleons it is being paired up. So there will be no any unpaired nucleons for this even nuclei. So for that case, the value of this total angular momentum J, so J will be equal to 0, and the parity will be always positive. So for example, if you have to find out the value of this ground state spin for this carbon 612 and oxygen 812, no, for carbon 12, so there is 6 proton and 6 neutron. So 6 means 2 nucleons, so it will be in 1s 1/2, and the other 4 it will be in 1p 3/2. So there is no unpaired nucleon, so their total ground state spin will be equal to 0, and parity will be always positive. So for even nuclei, so their total angular momentum that is equal to 0. So here comes our next. So for even odd or odd even nuclei, so for example, if I have to find out the ground state spin for this 3 helium 7 nuclei, now in 3 helium 7 nuclei, you will see there are 3 protons and 4 neutrons. So here you need to remember one thing. We have to consider only those proton or neutron which are unpaired. Like here n, that is even number, so it is completely paired up. So their spin will be cancelled with each other. So we will find out the spin from this proton number only. So by considering this proton number only, now you will see that there are 3 protons. First 2 proton, it will be occupied in 1s 1/2 orbital. Then after that, this last unpaired proton, it will be existed in 1p 3/2 orbital. So from that you can see that the ground state spin of this lithium 37 will be equal to 3/2, because this nucleon it is present in p 3/2 orbital. And how you can find out the parity? So parity you can find out from this value, -1 the power L. So L is our angular quantum number. So you will see that this last unpaired nucleon, it is in the p orbital, and I have explained you L, which varies from 0, 1, 2, 3, 4. So when it is in the s orbital, L is 0. It is in the p orbital, L is 1. So for this, we will consider L is equal to 1. So from that, we can find its parity, it is coming out to be negative. So we can represent its ground state spin something like 3/2 power minus. So this power, it is representing the parity of that nucleon's state. So similarly, for this carbon 613, you can find out the ground state spin. So here you will see there is even a number of proton. So they are being paired up, so they will not play any role in order to find out the spin. So there are 7 number of neutrons. So first 2 neutron, it will be goes into 1s 1/2 orbital. Then it will be occupied 1p 3/2. So then 4 nucleons, it will be occupied within this subshell. So total there are 7 nucleons. So 7th neutron, it will be goes in 1p 1/2 orbital. So we have to consider which state, so where our last unpaired neutron it is present. So last unpaired neutron it is present whose spin is 1/2. So we will write the value of J as 1/2, and it is present in p orbital, so parity will be minus. So ground state spin and parity for this carbon 613 is J1 by 2 minus. So this is how you can find out uh, of any given nuclei the ground state spin and parity. And the major limitation of this shell model that it failed to explain the spin and parity of odd nuclei. So later it has been further explained by Nordheim rule. So if both proton and neutron they are having odd number, then you can find out the spin and parity using this Nordheim rule. Now what this Nordheim rule says, you have to sum up all those four terms. Jp, that is representing the total angular momentum of number of proton. Jn, it is representing the total angular momentum for neutron. L is representing the orbital quantum number for proton. Ln representing orbital quantum number for neutron. And if the value of this whole sum, if it is coming odd, then we have to consider this J value for our final ground state term. And if it is coming even, then we have to find the magnitude of this value as our total ground state spin. And parity we can find out from the Ln plus Lp value. So let us do a numerical related with this. So for example, we have a problem that is boron 510. So in this case, you will see that there are 5 neutron and 5 protons which are present. So first 2 will go in one S1 by 2, and then last 3 they will go in 1p 3 by 2 orbital. So the value of Jn, it will be equal to 3 by 2, because these last unpaired neutron, it is present in 1p 3 by 2 orbital. So Jn will be equal to 3 by 2, and it is in p orbital, so Ln will be equal to 1. So similarly, same is the case for proton. So Jp and Lp value will be same. So when we add up all these 4 terms, and it is coming out to be 5. So 5 is an odd number, and according to our rule, if it is having a odd value, then we have to consider the total angular momentum, which is equal to Jp plus Jn. So then we will use this formula. So Jn is 3 by 2 plus Jp is 3 by 2. So when we add up, so our total J value, it is coming of the order of 3. So parity Ln plus Lp, so that is 1 plus 1, that is minus 1 is to power square, so it will become even parity. So our ground state spin and parity for boron 510 will be equal to 3 plus. So this is how you can solve such problems. So let us try to do some important problems. So we have to find the spin and parity of this ground state nuclei. So selenium, whose atomic number is 21 and mass number is 41. So how you can find out? So you also try to solve it. I want to check whether you have followed my concept or not. So you can write here the formula. Spuds if pug dish of pig. Remove all the vowels and try, because you will see that it is not a high atomic number, so we will go up to this sequence. So S, P, D, S, F and P. So let us try to study this. So सबसे पहले क्या आएगा 1s 1/2. So p it is being broken up into 3/2, 1p 1/2. Then there is d orbital. So there is a interfusion between this. So 1d 5/2. Then there is 1s which is in between this d orbital. And after that there is 1f 7/2. And there is also interunion between this. उसके बाद आएगा 1p 3/2, then 1f 5/2 and 1p 1/2. Now let us try to occupy. So in this there will be 2 nucleons. Here there will be 4 nucleons. Again 2 nucleons. So you can find out using this formula how many nucleons will be present. So again here there will be 6 nucleons. So here 2, here 4. So let us try to compile. So here you will see my proton number is 21 and neutron number is 20. So neutron number is 20, so it will having no role in order to find the ground state spin. So I will consider only the role of proton. So from that we can, because the last unpaired proton will give us the ground state spin for our this nucleus. So let us add it. 2 plus 4 6 plus 2 8, 8 plus 6 is 14, 14 plus 2 is 16, 16 plus 4 is 20, and I have 21 proton. So last unpaired proton will be present in this orbital 1f 7/2. So from this my J value, it is coming out to be 7/2. Now I have to find the parity. So parity is -1 to power L. So it is present in F orbital. So L will be equal to 3, because I have explained you for 0, 1, 2, 3. This is S, P, D, and F. So it is present in F orbital. So L will be 3. So -1 raised to power 3, it is having negative parity. So my ground state spin and parity for this selenium will be equal to 7/2 minus. So similarly you can find out for this nickel 2857, and this is your homework, and you have to tell me what is the ground state spin and parity for this nickel 2857. So next question, that is in gate 2000. So oxygen 815, it is having 1/2 minus. So you can see that, so there is only one option whose value is this. So similarly you can also solve this for oxygen 817. Now here there are 9 neutrons. So you will see that in 1p 1/2 two neutrons will be occupied, and after that there is 1d 5/2. So total we have 9 number. So last unpaired nucleons will be present in this case. So for this oxygen 817, J is 5/2 and it is in d orbital. So parity is even. So correct option for this question is 1/2 minus 5/2 plus. So this is the explanation I have written. So this is another problem. According to shell model, the spin and parity of two nuclei, antimony 51 and strontium 38, 89, 89 respectively, we believe. So antimony is 51 and 125. So you will see that proton number is 51 and neutron number it is coming out to be somewhere 49 plus 25. So neutron number is 74. So this is a even number, so it will not play any role. So from this proton number we can find out that what will be the ground state spin and parity. So this you can check. So using this same formula as I have told you, and you will find that the correct answer for this case will be 7 by 2 plus. So this, you try this question, so then we will see so whether you can solve it or not. So students, try it. Then I will explain. So you have 2 minutes, try to find, so whether you are able to find the value 7 by 2 plus or not. And similarly for this strontium, you will see that there are 38 and 89. So here proton is 38 and neutron is 51. So in first case, there are 51 protons and here there are 51 neutrons. So both will be having same spin. Are you trying? Students, are you trying?
Yes, sir.
Yes,
Okay, do. I am waiting for your answers.
sir. Yes.
Sorry?
Sir.
Yes? You got that?
Sir, it's 1G 7 by 2I. Yes, sir. Unpaired is in 172 orbit.
Yes, the last unpaired neutron or proton, it will be present in 1G 7 by 2. And from that, the J value, it is coming 7 by 2. And for G, you have to find, so G, L is equal to 4. So L is 0, 1, 2, 3, and 4. So it is S, P, D, F, and G orbital. So G, so L will be considered as 4. So parity will be equal to positive parity. So that's why our ground state spin and parity will be equal to 7/2 plus for both the cases, because in first case there are 51 protons which will play the role to find the ground state spin, and the second case there are 51 neutrons, so which will play the role to find out the ground state spin and parity for this problem. So correct option is option D. So next question is, the single particle energy difference between p orbital of the nucleus is 3 mega electron volt. The energy difference between 1f orbital, now what is given? So there is given that for this p orbital, so this is 1 p 3/2, this is p 1/2. So this energy difference, it is given 3 mega electron volt, and we have to find the energy difference between 1f orbital. So f will be broken up into 7/2 and 5/2. So this you can calculate the value of E, so that comes out to be h bar omega. So higher energy, so E of higher minus E of lower energy. So higher किसका आएगा? So इसमें, so how much value it has? So that is of the order of I plus 1 minus I. So in some books, J is also related with I, so which is representing the total angular momentum. So I plus 1. So here, this is having higher energy as compared to this. So P 1/2, it is having higher energy as compared to P 3/2, and energy difference is 3. And when you put the value of J, so J for this is 1/2 into 1/2 plus 1 minus 3/2, 3/2 plus 1. So it comes out to be 3/2 into 1/2, that is and this is 3/2 into 5/2. So I will write it here. So this 3, it comes out to be h bar omega into minus of 3. So what does it mean? So we can find out the value of h bar omega, so that comes out to be -1, and now we will use it for the f orbital. So that will be equal to 1f 5/2 minus 1f 7/2. So that will be equal to h bar omega 5/2 into 5/2 plus 1 minus 7/2 into 7/2 plus 1. So when you solve it, so it is coming out to be h bar omega. Now we know it is of the order of -1. And when you solve it, it is 5/2 into 7/2 minus 7/2 into 9/2. So it is coming of the order of -1 into -7. So that is of the order of 7 mega electron volt. So energy difference for this f orbitals, so that is of the order of 7 mega electron volt. So this is how, as we are going for upper energy levels, so the energy difference, it is increasing. So like for p orbital, the energy difference between 1p/2 and 1p 3/2, that is of the order of 3 mega electron volt. So you can also calculate from these calculations. So once one of the energy difference is given, from that you can also calculate the energy difference of other orbitals as well. So this is our last question for our today's lecture. So I will raise this. So this question is saying, let us approximate the nuclear potential in the shell model for a three-dimensional isotropic harmonic oscillator. So which of the two nuclei having magic number of protons and neutrons? So from these given examples, so which is having magic number of protons and neutrons? So if you solve for this, here in this 2 protons, and when you subtract 4 minus 2, there are 2 neutrons. So similarly in oxygen, 8 neutron and 8 protons. So I think, so you got your answer. So proton and neutron, 2 is a magic number, 8 is also a magic number. So option A is the correct option. So you can also counter verify other examples, like in this case, their proton is 1 and neutron is 1. Here in beryllium, proton is 4, neutron is 4. So both are not magic numbers, so this cannot be the option. So in this case, proton is 2, neutron is 2. Beryllium, proton is 4, neutron is 4. So this is not a magic number. So this is not also the correct option. So you can find out the magic number, and there are some other nuclei which are known as doubly magic nuclei. Doubly magic nuclei, they are more stable as compared to magic nuclei. So doubly magic nuclei are those nuclei whose proton and neutron both are having magic number values. So sometimes there is a question, calcium 2040 and calcium 2042. So which has having more stability? So you will choose this calcium 20. It is more stable as compared to calcium 2042, because in calcium 2040 it is having proton and neutron both are having magic number, so it is more stable as compared to rather this in which only proton is 20 and neutron is 22. So 22 is not a magic number. So these calcium 2040 is known as a doubly magic nuclei. So dear students, so this is all about for today's lecture. So if you have any doubt, you can ask me.
Sir.
Yes.
Hello, sir. Sir,
Yes,
in one of
yes.
slide, you said this, in a nuclei, in orbit of nuclei, there is no interaction between two nuclei. Nuclei are independent, right?
Yes.
So what about the interaction between proton and proton?
Actually, when this model it has been given, so they do not consider any sort of interactions, but later as still lot of people they have given modified models of these, and they have said that it is not possible, that you cannot assume that there is not any sort of interaction which exists between these nucleons. So there is of course some sort of interactions which are present between this proton and proton, but this model, when it has been explained, or when this model in 1933 it has been published, at that time they have considered some assumptions, and based on those assumptions they have proposed this model. But later on there are some like other modified versions of this shell model, like the Nielsen model, you can see the unified model, so which are more advanced models of most advanced version of this shell model. And there are some of the limitations we will discuss in our tomorrow's lecture. So what are these limitations of this shell model, and those limitations which have been covered by some other models. So every model, when it comes with time, so other people's come, so they say that this is not the correct way to explain this, so it can be something like this. So of course there are some sort of interactions which are present within these nucleons, but at that point of time when they have published, so they said they consider, they assume that there is no some sort of interactions which exist.
Okay, sir.
Of course, there are interaction. Otherwise, it's not possible.
Yes, sir.
Yeah. Yes. Any other question? So from competition point of view, I would like to say you remember this formula, so which is very, very important. So this is very important slide. So that's why I have written. And once you remember this formula, from that you can easily find out the ground state spin. And further, like in our tomorrow's lecture, we will discuss how to find the magnetic moment and quadrupole moment. And in order to find the magnetic moment, we need to find the value of this J. And the value of this J you can find out from this formula. So it is not like they always ask you for the ground state spin of a given nuclei. They can ask you find the magnetic moment of this particular nuclei, find the quadrupole moment of this particular nuclei. So once you are able to find the value of this J, so then you can find out all those other applications of these shell models.